Okay, symmetric matrices. Whenever you're, well, I'll give you the definition. A matrix, a square matrix, is symmetric if, and I should name the matrix, I'm going to name it A for originality, a square matrix A, I put it in the wrong place, a square matrix, namely A, is symmetric if A equals its transpose. So if the same, it's almost like you can fold it along the diagonal and it lays down on itself. So you know those butterfly pictures you make when you're a little kid? You squirt the paint on it and you fold it in half and open it up and it looks the same on both sides. That's a symmetric matrix. It's down the diagonal. You know, you can have any numbers down the diagonal because the diagonal is sort of out of bounds for the symmetry. Suppose you have 1, 2, 3 down here. But if I have, 8, 10, and 12 in those places, then I have to have 8 and 10 and 12 there, so that when you fold it across the diagonal, it's the same number. In other words, every row 1 is the same as column 1, and row 2 is the same as column 2, row 3 is the same as column 3. The transpose is equal to itself. That's a symmetric matrix. So if I looked at this, I don't think I would name it, and that's what I would call it, a symmetric matrix. It's got symmetry around the diagonal. So, it's a good name for it. So this is the definition, and anytime you're trying to prove something about symmetry, you're going to try to prove that a matrix is equal to its transpose. If you're trying to prove that matrices are symmetric, that's how you do it. Or if you're given A and B are symmetric matrices, that means A equals its transpose, B equals its transpose. You just use that definition. So, let's see. The following matrices are symmetric since each is equal to its own transpose. Okay, so far we've talked about diagonal matrices and what happens when you add or multiply and take inverses and transposes of the diagonal matrix. Actually, the transpose of a diagonal matrix is a diagonal matrix. Let's see, would it be itself? Yeah. Just be itself. So a diagonal matrix, by definition, would be symmetric. What happens if, so this is the theorem about symmetric matrices. So I'll say let A and B be symmetric matrices. Okay, so I've got two symmetric matrices. And I guess we have to define K being a scalar. Of the same size. And getting kind of far over here, but K is just a scalar, so just multiplying it by 5 or by a half or something. Well, this is kind of a duh, but then A transpose is symmetric. Well, that's just really a duh. If A is symmetric, then A equals its transpose, so its transpose would be symmetric. A plus B. So if I add two symmetric matrices together, so I have an example of a symmetric matrix. Here's another symmetric matrix, A, B, C. Now again, this might be a general matrix, but it's a general matrix for the 3 by 3 size. So this isn't a proof, but let's just fill in D, E, and F and D, E, and F. If I added those two matrices together, would the sum still be symmetric?
Should be.
Should be, yeah.
Yeah, because I'm adding 1 and A, D and 8, and E and 10, and if I do the column, 1 and A, D and 8, E and 10, and each row is gonna equal its column. So the sum of two symmetric matrices is symmetric. And furthermore, the difference, so the sum and the difference of symmetric matrices is symmetric. So it's something nice to remember. You know, if A and B are both symmetric, when I add them together, I get a symmetric matrix, or if I subtract them. What if I multiply one of them by a scalar? So if you multiply this matrix by 3, triple everything, is it still symmetric?
Yeah.
Sure. That's easy to see. Okay, here is, I think, the star for this one. The thing to remember. The product of symmetric matrices is not necessarily symmetric. Okay, so this is not a given. You can add them, you can subtract them, you can times by a scalar, multiply by a scalar. But A and B, AB, the product, is not necessarily, I don't know how to spell necessarily. There's only, I think maybe that, I don't know, symmetric. Okay, there is one case in which the product is symmetric, and that only happens if A and B commute. Okay, well, that's another word. Well, you know what the word commute means, but used in this context. And I'm sorry it's so low, but A, B is symmetric if and only if AB equals BA. Now we've talked about multiplying matrices, and you know, hopefully it's ingrained, that when you multiply matrices in the other order, it's not the same thing. The multiplication is not commutable, commutativity is not a thing for multiplying matrices. So, the product of two symmetric matrices is only symmetric if A and B commute. That's what, i.e., A and B commute. That means that you could multiply them in any order and you'd get the same thing. So if you have two symmetric matrices and you multiply them in the different order and you get the same thing each way, A times B or B times A, then the product of A and B would also be a symmetric matrix. But that's a pretty specific.
Can you not just look at the product and see if it's symmetric? Like, why would you then swap it and do it again?
Good question. I mean, doing this business is harder than just multiplying them together and looking at the product. So you're, in a practical sense, doing this test to answer this question isn't.
Okay.
Is probably more work. So let's see. Example 5, and I probably have time to do this. I want to make sure we have a good amount of time to talk about proof by induction today. Let's look at this. This is a specific example in the book. The matrix 1, 2, 2, 3. It's symmetric because the 2's are on the same place, and -4, 1, 1, 0. Okay, that's like A, that's like B. They're both symmetric matrices because the definition of symmetry, again, is that a matrix equals its transpose. Let's multiply them together, and we get -4 and 2 is -2, 1 and 0 is 1, -8 and 3 is -5, and 2 and 0 is 2. So this is the product. If this is A and this is B, this is AB. And think I can do this very well unless, I mean, I can, but I'm gonna rewrite them. This is BA this time. And multiply these together and I get -4 and 2 is -2. -8 and 3 is 5. 1 and 0 is 1, and 2 and 0 is 2. And this is BA. And these are not equal to each other, okay? So, in general, the product of symmetric matrices is not symmetric. Okay, this last theorem in this section, and then we're basically done. There's 2, I guess. Do I have, I'm on board. This is about symmetric matrices, and this theorem says if A is an invertible symmetric matrix, then A inverse is symmetric. So, if A is invertible and symmetric, then the inverse is symmetric, okay? So, prove this with me. Let's do a proof of this. Now, you probably remember from your geometry days that you have some given stuff. So this is called a direct proof. It's a pretty simple one. Here's what we know. A is invertible. So what do I know from this? I'm just gonna, there should just be sort of a knee-jerk reaction here. Anytime they tell you that A is invertible in a given, then you can use the fact that A inverse exists. So I'm going to write that down even though it sort of belabors the point a little bit, but I'm just going to say A inverse exists. I don't know how to spell this. And what does symmetric mean?
The transpose equals.
Yeah, and A equals A transpose. So this basically is taking what's given, the if stuff, and putting it sort of in this definitions. I'm going to use that. So I'm actually going to consider what A transposes. I'm trying to prove that A inverse is symmetric. So if I'm trying to prove this, I want to prove that A inverse equals A inverse transpose. That's what it means to prove something is symmetric. I want to prove that the thing equals its transpose. So if I'm trying to prove that A inverse is symmetric, I want to prove that A inverse equals A inverse's transpose. That's what I'm trying to get at. So let's take a look at this side of it that has more stuff, A inverse transpose. So I would probably start my proof just by saying A inverse transpose. So consider A inverse transpose. Well, we know that the inverse of the transpose is the transpose of the inverse. So we could say that's the same thing as A transpose inverse, because that was properties of inverses that we talked about before. But what do we know about A transpose?
It equals A.
It's also square.
It equals
No,
A
it's
equals A.
It equals A. Wait, am I going and saying?
That's inverse.
Oh, so yeah, because it's symmetric, A transpose equals A. And now we have, so that's the end of the proof. That little square means, and so it is done, or whatever, I don't know. So I have now proved that A inverse equals its transpose, even though I started with the transpose, because there's more stuff to do. The busier side, there's more stuff to work out. So that's a pretty simple little idea, is that I'm trying to prove that the inverse is equal to its transpose, and that proves that the inverse is symmetric. So you're just using the two definitions that you have. Okay, anytime you take, there's a formula to make a symmetric matrix. And I think I have room over here. Maybe I'll put it up here. Any matrix, A It doesn't even have to be square, could be non-square. Any matrix multiplied by its transpose produces a symmetric matrix. I'll just write it out. Multiplied by its transpose, no apostrophe, is symmetric. So in other words, A times A transpose, which also equals A transpose A, is symmetric. Whack. Okay, so in the book, I'm not gonna write this up, but they have a 2x3 matrix, and they just take the 2x3 matrix, they transpose it for a 3x2, and then they multiply them together, and it shows you that you get, you know what, this is not true. A transpose and, I should put and, because these, they're not necessarily equal to each other, but A times A transpose and A transpose times A are symmetric. They're, the product of a matrix and its transpose is symmetric. And this last theorem here, which is kind of a duh, if A is invertible, then A transpose the symmetric matrix would also be invertible. So if A is invertible, then A transpose and A transpose A are also invertible. So this little idea, if A is invertible, then A inverse exists. And if I take, and if A, and we also know that A transpose, let's see, if A is invertible, then its transpose is invertible. Did we talk about, that's an idea we learned earlier. We learned earlier when we talked about the transpose of matrix that if you just take all the rows and make them columns, or columns to rows, the invertibility of that matrix doesn't change. So if I have a matrix A and I transpose it, if A is invertible, then the transpose is invertible. Well, if A is invertible and the transpose is invertible, the product of invertible matrices is invertible. So the proof of this is just based on the product of invertible matrices is invertible. Okay, which is exactly what it says there. That's the end of 1.7. Now I'm going to hand out a worksheet. I don't know if anybody noticed, I've already posted it to Canvas yesterday, or yeah, whatever you call it. So pause